Hi there, it's Phys Powers, Coach Powers, whatever. Today we're going to be talking about heat and temperature. We're talking about chapter 14, section 1, specifically about temperature. We're going to learn how to convert temperatures and talk about what heat is and what the lowest temperatures are, all that sorts of fun stuff. So here we go. We're going to relate temperature to energy of molecules, and we're going to convert the temperature readings between Fahrenheit, Celsius, and Kelvin scales. So before we get started here, let's answer a couple questions and see if we understand something about temperature and heat energy. What does temperature have to do with energy? Remember that they're not the same thing, okay? So temperature is a measure of the average kinetic energy. And so you can have the temperature of something and it could be high energy or it could be low energy. You just have to realize that temperature is a way to measure a certain amount of energy, but it's average kinetic energy. So you could have some particles really high kinetic energy and really low kinetic energy altogether, and you would have the temperature kind of dealing with all of that, okay, because it's dealing with an average. We use 3 scales to measure temperature. We use our Kelvin scale, our Fahrenheit scale, and our Celsius scale. Those are the typical ones that we use in the science laboratory. Typically, we want to use Celsius and Kelvin, but here in America, we use Fahrenheit. How and why does a thermometer work? It works because of collisions, all right? We've talked about the kinetic molecular theory before, but the thermometer is working due to collisions. So keep that in mind as we continue to talk here. What does heat have to do with energy? Well, heat and energy are also not the same, just like temperature and energy are not the same. All right, there is heat as a type of energy, but it's not all energy, right? So we want to talk about what heat is and relate that to the overall energy versus just, part of the energy. And then what makes things feel hot or cold? In science, a lot of times it's kind of important to understand we shouldn't really be using the term cold because we're really just talking about relative amounts of heat energy when we talk about cold. All right, so temperature. We already said this, the measure of the average kinetic energy of the particles within an object. Remember that it does not depend on the number of particles. If I have 10 particles, I can get an average temperature. If I have, billions and trillions of particles, I can get an average kinetic energy, right? I can get a temperature with both of those things. They can have the same temperature, even though those 10 particles that hit you, you wouldn't have any idea that they were transferring energy to you at all because that's so few particles. But you could have a lot of particles hit you, and then you would realize, oh, I'm getting warm, because there are enough particles there to transfer energy to you for you to feel. So the thermometer uses expansion, and you can imagine inside that thermometer that there are tiny little, fluid pieces, right? So most thermometers today have like propylene glycol in them or maybe some alcohol. They don't usually have mercury in them anymore, but they have a liquid which can expand upon the collision of particles from the outside to the inside, right? And so particles strike the outside of that thermometer, and that causes the glass particles to vibrate and move, which transfers that energy into the particles of the liquid. And when the particles of the liquid get expanded, or faster, then they start to expand. And then as they expand, they move up the thermometer scale. And so then you see a change in temperature. And so thermometers work upon this principle of expansion of a fluid based upon the particles colliding on the outside. Digital thermometers will work, with similar concepts of collision, but they have nothing to do with the expansion of a liquid, right? So in a digital thermometer, you can have a solid, which is going to have all those collisions, and that's going to affect the small expansions of a solid that are inside. So what we see here is a picture of a thermometer on the left, and then you have some interesting looking thermometers on the right. Well, I'm going to show you a Galilean thermometer, which is basically what we're looking at here. So give me 1 second. Now I have this hanging up on my ceiling, and you may have never noticed it before, but it's been hanging up on that ceiling the whole time. that we've had school this year, right? And this is basically working on the same principles of expansion, right? If I collide with the particles of the air and have enough collisions with the outside of this glass, and that starts to cause the water on the inside to expand, okay? Now, each of these little bulbs have little they're all little floaties, and they have different densities. And they have different numbers on them. You can see this one says 75, that one says 80, that one says 85, this one says 70, this one says 65. And so if you get this water to expand enough, then it's going to lower its density. When it lowers its density because it's being heated up, then that means that the next ball is going to drop, right? And so the 75 ball will drop, and now you have the 80. So this is a really rough thermometer. It's only telling you the difference between 75 and 80 degrees. Right now, it's somewhere between 75 and 70. And as I'm holding it, that 70 is actually starting to float up a little higher than it was before, right? So it's actually causing some expansion because the particles in my hand are actually warmer than 70, and so they're starting to collide into this glass, and that's starting to expand the water and cause the density to change, right? Actually, and if it was really heating up a bit, this one would be dropping down. This is actually just, maybe my hands are cold. Maybe they're really cold. But let's look at the temperature of this really quickly. Let's see if we can figure out the temperature. We've got a neat little device here, which is a digital thermometer, okay, and it's an infrared thermometer. And so let's see if we can change the units on there. No, it's not changing the units, but let's look at it. Let's see if I can get a reading on this one. 23.2 degrees Celsius. Okay. 23.6. 23.2. Just getting a couple different readings. 23.1. If I can get the metal. 22.7. 22.1. So anyway, it's kind of fun seeing the different temperature amounts. If we convert that 23 or that 22 degrees, we'll be able to see that it's somewhere between that 70 and 75, okay, on the Fahrenheit scale. So anyway, fun stuff here. That's a Galilean thermometer. Here are those scales, and we can actually kind of take a look here. There's 20 and there's 30, and so here's 22, and you can see, yep, somewhere right in that zone right there that we're talking about, right? So these three scales are right next to each other. You can see that the red line is the same on all three. Okay, so the red line isn't changing locations. All we did is we changed the top and bottom numbers. Okay, and we might have changed the increments. Notice here the increments, they're showing every 10 apart are all about the same length as the 10 apart on this other side. So we go from 230 to 370. Okay, so that's a difference of 140. And you can see that from up here, we have a difference of 140 from there to there. But the increments on the Fahrenheit scale are a little bit different. We've gone from 220 all the way to negative 40. So we've gotten a difference of 260 degrees on this scale versus having the 140 and the 140 on these scales. Okay, basically what that means is that the size of a Celsius or a Kelvin degree is bigger than the size of a Fahrenheit degree. But it's also kind of nice and interesting to note that there's one place where the Fahrenheit and the Celsius scales are equal to each other, and that's at negative 40. All right, a little piece of trivia there for you. The basic degree to which they are different from each other, there are 9 Fahrenheits for every 5 Celsiuses. Okay, and you're going to see this little number here in a little bit, 9/5, which is equal to 1.8 Okay, you're going to see that number show up in our equation here in a little bit. And so there are 9 degrees Fahrenheit for every 5 degrees Celsius, and that's one of the ways that we're going to remember to convert and how we are going to convert between these different scales. Again, if we look at these scales, you'll notice that they're not really showing us exactly where our boiling points are. The water boils here on the Fahrenheit scale at 212. On the Celsius scale, it is 100. And then on the Kelvin scale, it's actually 373.15 is what they would like to call that, okay? Another thing that's important to remember about Kelvin is Kelvin doesn't have a degree sign. We do talk about degrees Celsius and we talk about degrees Fahrenheit, but we don't talk about degrees Kelvin. We just talk about Kelvin units, okay? In this system, we also have something called a ranking, and it's equivalent to Fahrenheit as far as the actual sizes of the degrees, but it actually goes and works kind of like Kelvin does in terms of how you could apply it mathematically, but we won't worry about that. So that's just extra facts for you. So here's our formulas. If we want to convert between the Celsius scale and the Fahrenheit scale, so we've been given degrees Celsius. Let's say I have 0 degrees Celsius. Then I can plug it into this formula, okay? I say 1.8 times the degrees Celsius, and this is a little bit goofy because the C is so far off, but basically that C would be right there. If I convert that 1.8 and I multiply it times 0 degrees Celsius, then that whole thing is going to be a 0, right? And then I add 32 to it. Now you guys have probably learned before that 32 degrees Fahrenheit is equal to 0 Celsius. Okay, now let's look at this one. If I have, let's say I have 32 degrees Fahrenheit and I want to convert it to Celsius. Well, 32 minus 32 is 0. 0 divided by 1.8 is 0. And so my degrees Celsius is 0 Celsius, so I'm at 32 Fahrenheit. So sometimes it's kind of hard to remember what these formulas are, but it is a little easier if you want to do the conversion. You can just choose some of the points that you already know. When you know that 0 and 32 are the same, then it makes it easy to convert between those two. Now, between Celsius and Kelvin, it's really easy. If you have Celsius, add 273. If you have Kelvin, then you subtract 273 to get your degrees Celsius. Okay. Again, so you want to double check that. You'd be like, okay, what's 0 Kelvin? That's absolute 0. We're going to talk about that in a second. Minus 273, then my Celsius is 273, negative 273 degrees Celsius. Okay, so that's that formula. If I were doing this formula up here, I'd be like, okay, well, what if I had 0 degrees Celsius? What is that in Kelvin? It's 0 plus 273, so my Kelvin temperature is 273. Okay, so these are conversion factors that you're going to need to be able to use in this particular chapter. Now, we want to talk about this concept called absolute zero. Now, this is really a fun concept. It's the temperature at which an object's energy is minimal. And I used to say that it was the temperature at which all matter stopped moving. But until tonight, when I did a little bit more research, I discovered that that's actually not true. I didn't know that until tonight. Because molecules, and again, your book actually says that it has zero energy, but the current research says molecules have vibrational energy due to quantum mechanical states, right? So they have this thing called a 0-point energy. And this was shown by a guy named Lev Landau back in 1941. And once you get down to these really, really, really cold temperatures, near absolute zero, then you start creating things like Bose-Einstein condensates, right? And this was something that was actually first created here at CU Boulder, all right, and here in Colorado in 1995. And when you have something like a Bose-Einstein condensate, you can get zero friction, and you have sound waves that are still, being, pushed off of this type of molecule. And so anyway, they've demonstrated that molecules do have vibrational energy at these really, really, really low temperatures. And so even though you might see at some point, absolute zero is the point at which all matter stops moving, the current research says, no, actually there is still vibrational energy. In the quantum mechanics state, you've always got some strange random things that'll happen every once in a while. And so you still have some motion that takes place. Anyway, really cool to look at. So let's look at some common temperatures. Now that we've had our our COVID world kind of changed on us, we see lots of different temperatures of our body, right? So 37 degrees Celsius is equivalent to 98.6 Fahrenheit and 310.2 Kelvin. All right, so these are just some common temperatures of things that you might be familiar with. The summer air in the desert, the metal in a running car, and dry ice are other things that you might be curious. What are the temperatures in different scales? So Celsius for summer air, 43, pretty hot, right? How hot is that? Well, that's 110 Fahrenheit, 316 Kelvin. Metal in a running car, if it's 115 Celsius, we're talking about 239 Fahrenheit, 388 Kelvin. And dry ice, which is really cold, negative 79 Celsius, which is negative 321 Fahrenheit, and 77 Kelvin. So this is really, really cold stuff, right? This is dry ice, which, at 77 Kelvin, we've only got, 77 more degrees to go back down below to hit zero, right? And so it's pretty cold stuff. There's not many things that are getting much colder than that, but there are. Again, we've never actually achieved 0 Kelvin. We've gotten within, billions of a degree of it. We're like 0.0000001, kind of temperatures. But remember, there's always energy from whatever vessel is causing you to refrigerate, right? To have you cool something down. That's always going to be putting energy in. And so it's impossible to get to this really, really, really super, super zero point, but we can get really close to it. Anyway, so what's the difference between heat and temperature, right? We've talked about temperature, and now let's talk about heat. The transfer of energy is basically the way we want to describe heat, okay? So it's a transfer. And why does it occur? It occurs because of differences in temperature. So if you have two different substances with different average kinetic energies, then the one that has greater kinetic energy is going to be striking the one that has lower kinetic energy, and it's going to be transferring its energy to it, right? And that's what we saw here, that objects with higher kinetic energy, the air, might be transferring to objects with lower kinetic energy, and so you're going to end up having heat transfer, all right? So that's a transfer due to differences in temperature. Now, remember that heat is always going to flow from the object that has higher temp to the object that has lower temp. It always flows in that direction. Okay, so this person is holding the glass of ice. The heat is going from his hand, or her hand, it looks like, sorry, into the glass, right, of ice water. However, if I have a cup of hot tea, then that hot tea is transferring the energy into the hand. And so it's always going to go from high temperature to low temperature. And when does it stop? It stops when the temps are equal. All right. So when you get those temperatures equal, that's when that is going to stop. Now, heat is dependent upon the number of particles. Now, remember, we said that temperature was not dependent on the number of particles. I could have 10 particles, or I could have millions of particles, and they could have the same temperature. That's not true for heat. If I have 10 particles and I have millions of other particles, then the millions of particles, if they're at similar temperatures, are going to have more heat. All right, they're going to have more energy. And so I'm going to be able to transfer more energy from this object that has millions of particles compared to the object that has just 10 particles. Now, an example of this, if I think about a lit match, it's going to have a really high temp, right? A lit match is going to have a higher temperature, but the hot tub is going to have higher energy, right? And so what kind of energy are we talking about? Heat. It's going to be that energy that it has that's allowed to transfer from one object to another, all right? So the hot tub is not going to have a higher amount of temperature, but it is going to have a higher amount of heat energy. So which has more heat, a swimming pool full of ice water or a cup full of boiling water? Okay, the swimming pool might be cold, but because it's got so many more molecules, the swimming pool has a whole lot more heat. All right, so much more water. It doesn't matter that the little teacup has boiling water. The one that has more heat energy, the overall number of particles moving, okay, think about all those particles in motion. The one that has more motion of the particles combined, not just how which ones are faster. The cup has faster molecules on average, but the pool has more molecules, so it has more heat. All right, so hopefully that helped you understand heat and temperature a little bit. Let's see if we can answer these questions. What does temperature have to do with energy? It measures the average kinetic energy. What 3 temperature scales are commonly used? Fahrenheit, Celsius, and Kelvin. What makes things feel hot or cold? Remember, it has to do with the transfer of energy. If I'm touching an object, that object is going to feel colder to my hand if my hand is transferring energy into the container, right? And I've got a really great demonstration to show you when you come in to class, but it's something you just actually have to see and feel to really appreciate it. So we'll wait till you guys get in class and I can show that to you. But it has to do with this hot or cold situation. And remember that the reason the tile feels colder on the bathroom floor is because the tile is sucking the heat energy out of your body, and the energy is transferring from your body to that tile. When you step onto the carpet, it does not seem so cold because that carpet is a good insulator. And so it doesn't allow for the conducting of the heat away from your foot and into the carpet nearly as well, because it's mostly filled with lots of little air pockets. So anyway, hope you've enjoyed learning a little bit about temperature and heat, and I hope you have an awesome day. Be kind one to another. Be kind one to another. God bless you. Have a good day.